Okay. Aditya is going to start with question 16.
So this is question 16 for people who didn't do the homework yet, but so this is from Mexico. So for people who didn't do the homework, I'll give you like a minute to look at it. Okay, so first, before we actually start trying to prove all the solutions, does anyone have a guess for what the solutions could be? Okay, yeah, so Alex said 1, 1, 1, 1. So that's the solution. So plus or minus 1 is not always going to be a solution here. Because if you plug in -1 for one of them, then the next one is going to be negative. The next one's going to be 1, and then A3 is also going to be 1, and then you're going to get a contradiction at the end. So I guess what you guys see here is that the only solution is just 1, 1, 1, 1. So to go about proving this, we're going to try to manipulate the equation in order to get some other expression that we can use. So first we can try adding 1 to every equation. So we get this equation when we add 1 to every equation. And so now we notice that the left side can actually be factored. So we can rewrite that as AI times AI plus 1 equals AI plus 1 plus 1. So this equation seems useful because we have similar terms on the right side and on the left side. And so what happens is that when we multiply all of these equations, the AI plus 1 term just cancels because it's on the right side in one of the equations and on the left side in another equation. So for example, if we take a product of all the equations, we have this. So now that we have this, we notice that the product on the right side is that AI plus 1 term on the left. So we can just cancel that out, and we get that the product of all the AI is just 1.
Wait, Aditya, I think -1 should work.
For
Like, if any of them are -1, then they're all -1, and then that's just another solution. That you assume, because you cancel that out, you're assuming like non-zero, right? And then like if you assume they're all not, that works. And then like
okay. Yeah, so so -1 is also a solution. And so after we cancel this out, so we have the product of all these is 1. And also, if we so another thing you might want to do is, if we want to try canceling out terms, you might want to try adding up all of the equations, because if you add up all of the equations on the right side, you'll just get a1 plus a2 plus a3 all the way up to an. And on the left side, you'll get the sum of the squares, and then you'll get the sum of the AI, and then you'll get minus n. So we can cancel out that term again. So now we're going to sum the equations. So if we sum all of the equations, then, as I said, we can cancel out a1 plus a2 plus a3 all the way up to an. So then we just get the sum from I equals 1 to n of ai squared minus n equals 0. So that sum is just n. And so now, given those two equations that we had, the product is n, and the product is 1, and the sum of the squares is n. Does anyone have any idea of how to relate those two? So yeah, Alex said AMGM, so that seems useful because we have a product of all the terms, and we have the sum of their squares, and we know all the squares are positive, so we can apply AMGM on them. So from AMGM, we can write that a1 squared plus a2 squared all the way up to an squared over n is greater than or equal to the nth root of a1, a2, all the way, the product for all the way up to an. And we know the product of all of them is just 1. So that side is, so the right side is 1, and we know the sum of the squares is n. So the left side is n over n, which is also 1. And so now this means that we have the equality case. And so in the equality case, we have to have that a1 squared equals a2 squared equals a3 squared, like that. So that's the equality case of AMGM. So And so now if we look at the equation that the sum of the squares was n, that means that, so if all the squares are equal and they all add up to n, that means that all of the squares have to be, all the squares have to be 1, which means that AI is plus or minus 1. But when we took the product and divided it out, we assumed that they weren't -1. So this just gives the solution where they're all equal to 1. And as was noted before, the other solution where they're all equal to -1 also works. So we have the solutions 1, 1, 1, and -1, -1, -1. And so those are our only solutions, and we proved it with AMGM. So does anyone have any questions?
If A1, A2, A3 all the way to AN is -1, it also works.
Yeah.
Okay, it looks like there's not many other questions, so I guess I'll take over for YCMA 2015. Question 1. So for everyone who didn't read this question, I'll give you a few moments to do so and think about it. And feel free to type ideas in the chat. So somebody is suggesting to expand. Expansion might work, but if we look on the right-hand side, we're taking the cube of a 3-term expression, and most likely expanding is going to give a lot of terms which we don't want to deal with. So we first have to simplify the expression a bit before we can expand. But it looks like there's no other suggestions, so I guess I will get started. So the first thing we can note, I guess, is that the left-hand side is definitely an integer, so the right-hand side is an integer as well. So what does that tell you about x plus y? Yeah, so x plus y is divisible by 3. So we have x plus y equals 3a, for example. So now the right-hand side is obviously going to be a plus 1 cubed. And we want to somehow write the left-hand side in terms of a. So let's try to find a good expression for the left-hand side in terms of x plus y. So Aaron is suggesting 9a squared minus xy. We don't want an xy because now we have 3 variables. So what we do instead is we set x squared plus xy plus y squared equals x plus y squared minus x plus y times y plus y squared. And now our only 2 variables are x plus y and y. So now we don't have to deal with p. Yeah, so the problem with p is that it's slightly annoying to work with because a is going to be a linear a linear variable and p is going to be a quadratic variable. And we don't want to mix them if we don't have to. So yeah, instead we're going to set x plus y equals 3a and then just cancel out the x using this identity. And this gives us that the left-hand side is y squared minus 3ay plus 9a squared. So now given this expression, does anybody have any ideas? Remember, we're trying to get integer solutions in a and y. And note that any solution we get for a comma y will translate into a solution for x comma y. So we haven't lost any information. So are there any ideas? Why is it a plus 1 cubed? Because x plus y is equal to 3a, so the right-hand side is inside the cubed is a plus 1. Yeah, so Eric suggested using the quadratic formula because we see that this expression is a quadratic in y. So what we're going to do is write it as a quadratic in y. So if we group up all the constant terms, we're going to get this quadratic, y squared minus 3ay minus a cubed minus 6a squared plus 3a plus 1 is equal to 0. And now we have a quadratic expression, and we want to try to see when it's an integer. So I'm sure a lot of you have seen this before. If we want this to be an integer, we need to have that the discriminant is a perfect square. So let's go to the next slide. And the quadratic yields an integer root, so we get that the discriminant has to be a perfect square. So let's go find the discriminant. For all of you unfamiliar with the term, it's just b squared minus 4ac. It's the number inside of the radical in quadratic formula. And we're going to denote it as delta. And when we, Brian, scroll down. Yeah, so the discriminant is going to be 9a squared plus 4 times the constant term. So 9a squared plus 4a cubed minus 24a squared plus 12a plus 4. And we get this ugly expression, which we want to be a square. So how are we going to get this to be a square? What's something which would be very nice about this expression if it were true? Yeah, factoring. It would be really good if this expression factored. So somebody asked, why is the LHS a triangle? The triangle stands for delta, which is how we normally denote discriminant. So anyways, can anybody think about how to factor the right-hand side? We probably want some linear factors, so it probably would help to find some rational roots using the rational root theorem. Yeah, so are there any obvious rational roots? Yeah, 2 is a root. In fact, I'll just give it away. 2 is a double root. So this this cubic actually factors as a minus 2 squared times 4a plus 1. So since we want this number to be a square, and a minus 2 squared is already a square, 4a plus 1 has to be a perfect square. In fact, 4a plus 1 is odd, so it has to be an odd perfect square. So we're just going to let it be 4n squared plus 4n plus 1, which is the form for an odd square. It's 2n plus 1 all squared. So this gives a is equal to n squared plus n. So now let's plug it back into our expression for delta. We get delta is equal to n squared plus n minus 2 squared times 2n plus 1 squared. So now when we plug it back into our formula for the quadratic formula, we get 3n squared plus n plus or minus the square root of delta over 2. And the square root of delta is an integer because we made it an integer. And note that throughout this entire process, we haven't lost any information because, well, when we made our substitution equals a, we still had all the information, and now we have that 4a plus 1 has to be a perfect square. So this is the only possible form of a, n squared plus n. So this means that when we find our solutions, these are going to be the only solutions for y. and the only solutions for y are y equals n cubed plus 3n squared minus 1, and negative n cubed plus 3n plus 1. So now I'll save you the trouble, but if you go back and find out how we defined n, how we defined a, ... we're going to eventually get that x is going to be equal to actually either negative n cubed plus 3n plus 1 or n cubed plus 3n squared minus 1. So actually x and y are just flips of each other, which should make sense because if you look back at the original equation, yeah, it's symmetric in x and y, which means that if xy is a solution, yx is a solution. So if random cubic in y is a solution, then random cubic for x should also be a solution. So that means that our final set of solutions is going to be x comma y is equal to n cubed plus 3n squared minus 1 comma negative n cubed plus 3n plus 1, or it's flip, where x comma y is equal to negative n cubed plus 3n plus 1, and y is equal to n cubed plus 3n squared minus 1. So yeah, this is a really ugly solution, and it actually is the full characterization of solutions, where n is any integer. So does anyone have any questions? Can I repeat the last part? So which part? About why x is what it is? The fifth bullet down. Okay, so what we're doing now is that we already have a is equal to n squared plus n. And we already have a formula for the discriminant. So we're just going to plug n squared plus n back into our discriminant formula to get that. And then how we got y is just using quadratic formula. Brian, if you scroll up a bit. So if you just look at the quadratic, not that up. Yeah, so if you look at the quadratic, we already have the correct form. So we'll just plug in b for b, whatever, and then we'll get it. Is there another way to do this problem? Yeah, like all Olympiad questions, there's a ton of methods to do this question. But most of them are this discriminant trick in some form. Like, you have to notice that the discriminant in some form factors. So a bit of theory behind this question, we see that our original expression is a cubic in x and y, which the general name for these kinds of equations are called elliptic curves. So elliptic curves are a pretty hard theory, and there's a lot of unsolved results about them. So the point is that if they put this on an Olympiad, it has to have a nice solution behind it. Because if they just gave you a random elliptic curve, there would be no way you can solve it. Yeah, Daniel told me that elliptic curve is degree 3 in one variable, degree 2 in the other. If you do some substitutions, you'll get it to an elliptic curve. I think that Aditya said x equals a plus b and y equals a minus b. I think that this will give an elliptic curve, but I'm not sure. Either way, the point is you have to find some kind of clever substitution just by the nature of, I mean, some clever factorization just by the nature of this question. So I think that all solutions to this question will follow some form of you get some stuff and then you factor at the end. Are there any other questions? Scroll down. Okay, are we good to move on? I guess so. So let's start with a bit of a preface. Last week was equations A, and throughout the entire class, we mostly talked about normal behaving equations. What I mean by that is that most of our equations were polynomials or systems of polynomials or something like that. So this week in equations B, we're going to talk about less commonly seen functions inside equations. We're going to talk about radicals first, then floors, and then finally logs and exponents. So these are the weird equations, you could say. So in these equations, there's a lot less theory behind them and more special tricks, or trying to reduce them back to the well-behaved equations we saw in equations A. So I guess we'll start with radicals. So these bullet points will make a bit more sense when we go to our actual example. But the key idea when we have a radical, such as a square root inside our equation, is to try to, well, if we have a square root, for example, we're going to try to square the sides until we get rid of the square root, because it's really hard to solve equations directly with square roots. And then, of course, minimize the number of powers you take. What this means is that if you have multiple square roots, you want to square things effectively such that you don't square too many times, or else your final expression is going to be not very good. And then always find nice substitutions. And finally, the problem with square roots is that they always have to be positive. So once you square stuff, you lose a tiny bit of information. So once you get all your equations, once you get all your solutions, you want to go back to check if they make sense in the original question. So without further ado, we'll get to our first question. So this question is from Math Prize for Girls. I'll give you a moment to read the question. And feel free to type ideas in the chat. So Aaron says we should square this, and actually we should. If you look at the bullet point above, we should always square radical expressions, just because it's really hard to deal with radical expressions otherwise. And then the point is there's nothing bad that can happen if you square it. So let's, okay, is everything good? Okay, so let's just square it. And now we're going to get a quartic. So yes, quartic formula exists, but none of us know it. So how can we possibly solve this question now? Okay, some people are suggesting rational root theorem. This is good. This is a really good idea if there are rational roots, but there are none. So that's not good. So Kevin says use Vietas. So now the problem is Vietas is going to give you all the solutions to this quartic. But do we want all solutions to this quartic? Remember we said that if we square stuff, we're going to lose some precision, which means that some of these solutions might be extraneous solutions. And if we get extraneous solutions, we don't know which ones are which. So that's not going to be good. So actually, because it says, because it started as a square root expression, this means that no Vietas will work and we have to find all four of the solutions, which means that there has to be some factorization involved. But it looks rather hard to factorize. So we're going to use a bit of a sneaky trick. We're going to try to make it a quadratic. So can anybody tell me how to make this a quadratic without substituting? No, x squared equals y won't work because we have an x term. So here's something funny. So if we look at 2015, 2015 has a squared, and 2015 is only squared. So why don't we make y equals 2015 and x the constant, as Kevin just told us to? Okay, now it's a quadratic. So now how do we solve this quadratic? Yeah, we just use quadratic formula. Even though 2015 is our variable, quadratic formula still works perfectly well. So let's go ahead and plug in, and we'll get that 2015 is equal to 1 plus 2x squared plus or minus, and our discriminant, if you expand it out, actually becomes 4x squared plus 4x plus 1, which is a perfect square. So actually, we were guaranteed that this discriminant will work out well because we knew that all of our solutions had to be nice, which meant, and there are no rational roots. which meant that the quartic had to be factored as 2 quadratics. And that means that both quadratics have to be nice, and hence our discriminant has to work out well. So now this gives us 2 possibilities for what 2015 equals. So if we scroll down to the next slide, we're going to get that either x squared plus x plus 1 equals 2015 or x squared minus x equals 2015 by either taking plus or minus. And then as an aside, as I said, note that this test tells you that the original quartic could be factored as as x squared plus x minus 2014 times x squared minus x minus 2015. But we got the factorization for free because we just set 2015 as the variable. So now let's just solve both of these quadratics. You guys don't need to do quadratic formula, I got you. And we get x equals -1 plus or minus square root 8057 over 2, and x equals 1 plus or minus square root 8061 all over 2. So now these solutions are good, but which ones actually work? So let's scroll up. So let's look at the equation. What does x have to satisfy in order for it to work? Well, not x is greater than 2015. Yeah, x has to be greater than -2015. But that's actually not useful because all of our solutions are greater than -2015. So actually what's useful is, as a lot of people are saying, x has to be greater than square root of 2015. Because if it's less than, then the right-hand side is actually going to be negative. And we can't have a square root is a negative. Oh yeah, as Kevin says, we can also have x is less than negative square root 2015. But I don't think any of the solutions are.
One of the solutions is.
Oh, did I mess up?
There should be one bigger and one smaller.
Oh yeah, okay, I didn't mess up. Technical errors. Okay, so yeah, never mind. So it's either greater than square root 2015 or less than square root 2015. And once you start computing it, as it turns out, one of them is greater than and one of them is less than. So our only solutions are square root are -1 minus square root 8057 all over 2 and 1 plus square root 8061 all over 2. And to easily see why the other ones don't work, the number inside the square root is around 4 times 2015. So if we square it, the number is going to be around 2015. But if the -1 goes in like the opposite direction of the radical, which means that like -1 plus square root 8057 or 1 minus square root 8061, once we square it, the difference is going to be way too big, and it's going to be within the threshold of square root 2015. So it won't work. So those are our only solutions, and we'll just add it and take a reciprocal. And that's just normal rationalizing the denominator. So floor of 1 over s is equal to floor of 2 over square root 8061 minus square root 8057. You rationalize and it becomes floor of square root 8061 plus square root 8057 all over 2. And then the top two terms are very close to each other. So really you just need to find floor of square root 8057, and that's 89. So are there any questions on this question? Yeah, so I think the most important takeaway is this. There's a quartic. Quartics are hard to solve, so we're either going to try to factor it or we're going to try to find a sneaky way to make it a quadratic. And then 2015 actually works really well. But actually, if you look at the factored form, it's not too hard to guess that it's going to be the factored form because our constant term was 2015 times 2014. So you might guess that the two quadratics would have constant terms negative 2014 and negative 2015, and obviously the two quadratic coefficients are 1 and 1. So guessing this factored form isn't too bad. Okay, I guess there's no other questions. This was actually our only example for radicals because we found them to be a bit of a one-trick question. You always just square it or something. And then there's a lot of other really weird tricks, but they're usually just case by case ad hoc. So we're going to move on to floors now. So as stated before, some equations are going to have floors in them. And what floors are, most of you probably know them, is just going to be the greatest integer not strictly, I don't know why I wrote that. It's the greatest integer less than x. If x is an integer, floor of x is just going to be equal to x. And then floor equations are usually bashy because floor of x is a very weird function to work with. So we're either going to do casework on floor of x, like setting floor of x equals some given integer, or we note that floor of x is going to be very close to x for big X. So we can try approximating floor of x as x, and then for the small values, we'll do them with casework. So yes, most floor questions are going to be casework, and the questions we have in this section are going to be pretty bashy. So let's get right into it. Our first example is 2019 HMMT November team. Some of you actually might have been here. So as usual, we'll give you a few moments to read. You can type comments in the chat. Yeah, so as a lot of people are noting, there's not that many cases. There's only 5, arguably 6 cases. So the first case we're just going to knock out is when, so let me just first type that out. So the first case we're going to knock out is when x is an integer, just because then floor of x is equal to ceiling of x. So what are the solutions when x is an integer? Yeah, so floor of x, so all of the numbers inside the floors and ceilings are all integers, so they're actually all solutions. So our solutions for x are 1, 2, 3, 4, and 5. So now what remains to be checked is when floor of x comma ceiling of x is equal to 0, 1, 1, 2, 2, 3, 3, 4, or 4, 5. So let's just go in order. What happens when it's 0, 1? Remember that since we already dealt with the integer case, now we're assuming that x is always non-integer. Yeah, there's no solutions. So what we get is that the denominator is 1, which means that the right-hand side always has to be an integer. But we don't want the right-hand side to be an integer. So no solutions. Now let's look at 1, 2. So when we plug in ceiling of x equals 2 and floor of x is equal to 1, our expression becomes x is equal to the ceiling of x squared plus 2 all over 3. And then because x is between 1 and 2, x squared is between 1 and 4. So now what can x be now? Yeah, so because ceiling of x squared is between 1 and 4, we'll just check if it's 2 or if it's 3. I mean, if it's 2, 3, or 4, and then that gives x is equal to 4/3, 5/3, or 6/3. And it can't be 6/3 since we're assuming integers. So numerator has to be 4 or 5. And actually, Christopher, both 4/3 and 5/3 do work. So we can check this. If x is equal to 4/3, we get 16/9, and the ceiling of 16/9 is 2. Yeah, you might have thought it was floor. So ceiling of 16/9 is 2, so 2 plus 2 over 3 is 4/3. And 5/3, if we square it, becomes 25 over 9. The ceiling is 3, so now 2 plus 3 over 3 is also 5/3. So 4/3 and 5/3 work. That's interesting. Now let's do 2, 3. Let's see what we get. It's on the next slide. So we get x is equal to the ceiling of x squared plus 6 over 5. Yeah, so now let's do the exact same thing. So the ceiling of x squared has to be 5, 6, 7, 8, or 9. 9 doesn't work again. So this numerator is going to be 11, 12, 13, or 14. So that means x is going to be 11/5, 12/5, 13/5, or 14/5. And then let's quickly check. So 11/5, if we square it, we get 121 over 25. The ceiling is 5. And then 5 plus 6 over 5 is 11 over 5. So 11 over 5 works. And then we'll check 12/5, 13/5, and 14/5, and we actually get that all of them still work. So now we're probably a bit suspicious. It looks that like everything we're getting so far is working, besides 0, 1. But if we try to apply the same thing for 0, 1, we actually get that there were no solutions to begin with. So yes, everything does seem to be working. So let's try general n and show that everything works. But yeah, if this was in contest conditions and you saw this, feel free to engineer, because this is pretty convincing at this point that we are going to get that everything is a solution. But since we're YCMA, we're going to prove it. So for general n and n plus 1, we're going to let x equals n plus k over 2n plus 1. And k, of course, is between 1 and 2n. So now what we want is to find ceiling of x squared. So we're going to compute ceiling of x squared first. And x squared is equal to that first binomial expansion, n squared plus 2nk over 2n plus 1 plus k squared over 2n plus 1 all squared. And then now what we're going to do is we're going to split the 2nk over 2n plus 1 term as k minus the fraction k over 2n plus 1. So now we want to find the ceiling of this. Does anybody know what the ceiling of this nasty expression is? So I guess one thing we can do first is we see k over 2n plus 1 twice on the right. So what if we let y equals k over 2n plus 1? Note that y is between 0 and 1. So the right stuff is actually just y squared minus y. And it's not hard to see by whatever inequalities you want to use that y squared minus y when y is between 0 and 1 is always between -1/4 and 0. And in fact, I don't think you'd even need this tight of a bound. It's really, really easy to show that it's between -1 and 0, because negative y is positive, and negative y is negative, y is greater than or equal to 0, and y is less than 1. So that just tells you that y squared minus y is greater than -1, and it's obviously less than 0. So what we're doing is we're taking an integer, n squared plus k, and we're subtracting a number, and we're adding a number between 0 and -1, which means that the ceiling is just going to be n squared plus k. Does that make sense? Okay, no questions, I guess.
I think it should be -1/4 less than or equal to y squared minus y, but
Oh yeah, it's
that big of a difference.
non-strict, but yeah, the important thing is that we just need -1 is less than it. So now it's -1. So now we just get ceiling of x squared is equal to n squared plus k, and remember that x is equal to n plus k over 2n plus 1. But if we write it in the form we want, it's going to be n squared plus k plus n squared plus n all over 2n plus 1. So this is just combining under the fraction and under a common denominator, and we know that n squared plus n is just floor times ceiling. So that means we want ceiling of x squared to be n squared plus k, and we just got that it was. Can I explain why ceiling of x squared is equal to n squared plus k? So we got that x squared was equal to n squared plus k plus some number between -1 and 0. So n squared plus k is an integer, and we're adding some small number which doesn't change the ceiling.
We're subtracting it.
I'm saying adding a number between -1 and 0, but yeah, sure, subtracting a number between 0 and 1 is probably easier to understand. So we're subtracting a number between 0 and 1, which means that it's not big enough to change the ceiling. So ceiling of x squared after we subtract y minus y squared is still going to be n squared plus k. Okay, so then once we look back at x, we see that we wanted ceiling of x squared to be n squared plus k. So that means everything works out perfectly. So in particular, this means that all k work. So let's summarize what we have right now. So we have that, it's on the next slide, we have that our solutions are the integers as well as the fractions between n and n plus 1 with denominator 2n plus 1 for n equals 1, 2, 3, and 4. So the question asks for their sum. So let's calculate the sum of fractions with denominator 2n plus 1 first. So that's going to be n plus 1 over 2n plus 1 plus n plus 2 over 2n plus 1 plus n plus 3 over 2n plus 1 all the way to n plus 2n over 2n plus 1. And then if you take out all the n's, there's 2n of them. So the first term is 2n squared, and the second term is just going to be 1 plus 2 plus all the way to 2n all over 2n plus 1. I'll take a moment for you guys to digest that. And then the numerator we just sum is n times 2n plus 1. So our final answer is 2n squared plus n for each n. So now let's just sum everything. Our final answer, first let's add all the integers, 1 plus 2 plus 3 plus 4 plus 5. Then 2n squared plus n. 1 plus 2 plus 3 plus 4 plus 2 times 1 squared plus 2 squared plus 3 squared plus 4 squared. And that's 85. And then remember that because this was on an actual competition, if you didn't feel like doing all the proof in between and you solve the first few examples, you could easily engineer to get this. So are there any questions? Okay, I guess I will turn it over to Brian. Oh, wait, no, I guess we're going to take a 5-minute break right now. So, yeah. You can continue.
Okay, so if you, we're going to go on to the next question, I guess. So, there. So our next question is from the 2012 H1P test. So I'll give you a few minutes to think about it, and then we'll discuss it later. Also, of course, if you have ideas, you can type them in the chat. So someone had the idea of taking the product of everything. So yeah, sure, let's try that. So if we take the product of everything, yeah, so if we take the product of everything, we should get that equation, right? And then, well, we kind of see that floor of A, floor of B. Well, we see that we have something that resembles ABC. And then so we kind of just express it in terms of floor of A, floor of B, floor of C, because if we should think about it, this has less possibility than just ABC. So, well, we just see that this is 60 is at least the product of the floors cubed, which means that, well, what does this tell us about the product of the floors? Like, what can we say about floor of A, floor of B, floor of C? Yeah, well, so we knew it's an integer, but yeah, it's also at most 3, right? Because if it were like 4, then we would have 64, but 64 is not less than or equal to 60, right? So we would have that this is true. Right, so, well, this is a pretty restrictive statement, right? Because we already know that, like, we know that this is basically saying the product of 3 integers is at most 3. So this is like a very strong statement. So yeah, at least 2 of them are 1. Because
well, actually, some of them could be 0, but that's not a problem because they won't satisfy the original.
Yes. So if any of them are 0, well then, like, let's just say floor of A is 0. Well, we already know floor of A times BC is 3, right? So if floor of A is 0, then we get that 0 is 3, which is clearly false, right? So we get that they're all positive, right? So, and then if any of them are, if we have 2 of them are at least 2, well then we have 4, something that's at least 4 is on the left side, but we also know that it's at most 3, so that's not right. So we need that at least 2 of them are 1, right? So we have at least 2 of them are 1. There, and then so, well, this is even more restrictive, right? And then so from here, we can do some casework on which ones are 1, right? So, well, we'll first start with the case of all of them are 1, right? So, well, if the floors of all of them are 1, then what does this tell us? Yeah, we get that equation. And well, so this is actually a pretty common equation, I would say, something of this form. And so it's a good idea in general to know how to solve this type of equation, right? So from here, we just, yeah, we multiply it and then square and divide, right? So yeah, because the idea is we have symmetric equations, so we want like symmetric expressions to go with it, I guess, right? And if we could get ABC, that would be really nice. And
yeah, just a quick note, on the other hand, you could just do AB equals 5 implies that either A or B is greater than 2.
Yes. Oh yeah, this is definitely better because, well, this simplifies the casework, but like if you didn't hear, like AB equals 5 means that at least one of them are at least one of A and B is at least 2, right? But then we already assumed that the floors of all of them were 1, right? So this doesn't work. But the idea here is also, more importantly, to figure out, like, to learn how to solve this general type of equation, right? Because it's a common type of equation, and it's useful to know how to solve it. So we'll solve it for this case, because the other cases are actually just similar to this one. So if we were to solve for A, B, and C, which, as William noted, is not necessary in this case, we would get this set of values, right? And then, of course, like, we should have this on the next slide, shouldn't we? It should be on the next slide. Oh wait, I moved the wrong one, never mind. But we'll just stay on the next slide, I guess. So, well, yeah, if we were to, like, look at all of them, then their floors would not match what they're supposed to be.
In
So
particular, the floor of C is too big. The floor of C is 2.
yes, because, like, 15 is bigger than 9, I guess you could see. So square root of 15 over 3 is greater than 1. So this doesn't work. So,
I
well,
think that these numbers are in the wrong order, right? Not
they
that
are in the wrong order. This is true.
Oh, yes, they are.
Yes. But the idea is the same. They still don't work. Well, let's fix that. But regardless, they still don't work. Because of this, right? As we said a few times, right? So it doesn't work. So that just means we'll have to move on to the next case. And then the next case, well, so the cases are all actually similar to the first one, in that we just have to solve this type of equation again, right? And, well, wait, do you want me to go over, like, the solving of each of them? Because it's pretty, like, boring and non-instructive after you, like, from this point on.
do,
Because
like, one more, and then
we'll do this case, just so that, like, we see one that works. So yeah. And, well, in this case, we have it cut off a little, but that's fine. So yeah, in this case, we have that's the solution, right? And this is great. But we still have a lot of casework to go through. Like, for example, if floor of C was 3 instead. And then this is another case that fails. Do you want me to go into details about it? It's like you just use the same, like, you use the same way to find ABC as we did earlier, but then you just have to check all the floor conditions and make sure that they work or they don't work. So it's not very instructive at this point. So we'll just, unless you guys really want to do it, we'll move on to the next question. So is that fine with everyone? Yeah. Okay, yeah, let's move on then.
yeah, okay, I guess this question just shows how, like, bashy floors can be,
Yes.
because we have 6 cases, but they're all identical. And yeah, as Aditya said, the full solution is on the handout.
The official solution on the HMT website is a little bit cleaner because they managed to take out half the cases with another floor estimate. but it's a bit tricky and we didn't include it here.
Yeah. So I guess we'll move on to this Amy problem. So I guess if you guys want to think about it for a bit, you guys can like say ideas.
Well, there are technically 6 cases for that problem. They get it down to the floor of A times floor of B times floor of C is at most 2. So the only possibility is 1, 1, 2. In our cases, we also have the possibility 1, 1, 3.
Yeah. In general, you can do more clever arguments that remove more cases, but then this is also more work. So like depends on how you'd want to do it because it still is some casework at the end of the day. But yeah, does anyone have ideas for this problem? So we could bash through small numbers, and if this were in actual context, this would not be such a bad idea. But this like is not as instructive. This is not. Oh, this is from a contest. Like if you were taking the 2012 Amy 2, yeah, then yeah, sure, you could do that. But we're not currently taking the 2012 Amy 2. So we will not just bash through it. So I guess I'll just start. So Kevin had the idea of what if we wrote x as a mixed fraction, right? So well, this is like this is a good idea, right? We want to basically express x in terms of a fraction, right? But like how we do that is not like so we want x as a fraction, but then so we have that n and floor of x are both fractions. No, are both integers, I mean, sorry. So and x is easily bounded by floor of x, right? So that's our general approach here is we want to bound n by using bounds on x and floor of x. So if we let k equal floor of x just for ease of typing, I guess, then we'll see that this is true, right? Because like floor of x is always at most x, but then x is always less than floor of x plus 1, right? So if we just replace all that stuff with k, then we can get this really nice bound in terms of bound on n in terms of k, right? And this is actually very useful, right? Because this essentially reduced it down. Wait, you guys shouldn't be allowed to annotate. I thought I turned that off.
No, it's fine. I just turned it off.
Okay. So anyway, we should have we have this nice inequality on n, right? And then so with this inequality, well, what does this tell us, right? Well, so basically, let's just try plugging it back in now. So well, if we have this value of n and then x is like just n over k, well then we see that this actually works, right? Do you guys want me to like explain that slower? Like the general idea is, well, we know we know n and we know floor of x, right? And then so well, we just see that x is n over k, and then we just we see that this is true, right? So I guess we won't. That's like kind of it for this problem, and then the rest is just counting how many of these there are. Well, so the thing is, floor of x can't be 0 because we kind of just floor of x starts at 1 and k starts at 1.
Well, the
Because
floor of x is
otherwise-
0. Yeah, floor of x is 0, then n is 0, and that's not
Yeah,
positive.
because otherwise it's not positive, right? So we'll just ignore that case of floor of x equals 0. Yeah, so can you guys not talk about William's AF account right now? But like, yes. Does anyone have questions on that question? Okay, doesn't look like it. So in that case, I think I'll pass it to Aditya. I think is going after me, right?
Yeah.
Yes.
So I'll give you all a moment to think about this question. Okay, so does anyone have any ideas for how to start? So Kevin is suggesting to write a substitution. So we're gonna do it similarly, but it'll be slightly different. And yeah, I wrote this problem a few years ago. So the key thing to note here is that floor of A is an integer. So we can actually try to isolate all of the terms with floor of A on one side. So if we do that, the equation should rearrange to 4a squared equals floor of A to the 4th plus the floor of A minus 1. So yeah, so 4a squared has to be an integer here. And we can do more. We can actually just solve for what A is in terms of floor of A, right? So if we divide everything by 4 and take the square root, we get A can be the plus or minus of the square root of floor of A to the 4th plus floor of A minus 1 all over 2. And so now this is good because this is going to be really useful because, as Brian said, we can use bounding. So when floor of A is really big, what do you think happens to the expression we have for A? So yeah, so the right side is a lot bigger than the left because when floor of A is large, the right side is basically floor of A squared because we have floor of A to the 4th inside the square root. So floor of A squared is going to be much bigger than A, and so that's not going to work. So based on this, we have like an intuitive reason for why floor of A is probably going to be pretty small here when we're looking for solutions. So first, we're going to look what happens when we take the positive square root here. So on the next slide, so what Kevin was saying before was to do the substitution A equals floor of A plus the fractional part of A. And so the reason you do that sort of substitution is because you know that the fractional part is between 0 and 1, as we have here. So we can do bounding. And so if we take our expression for A and subtract floor of A, that has to be between 0 and 1. And So now, does anyone have any ideas what values floor of A can be? Remember that we said that we're taking the positive root, so that means A was positive. So floor of A is 1, so let's just try that. When that's 1, you get A is 1/2, and so you get 1/2 minus 1, and that's negative 1/2, so that's not going to work. Yeah, so Kevin says 2. And yeah, so when floor of A is 2, we get that it's the square root of 17 over 2 minus 2. And so that's between 0 and 1. So that works. And does anyone think there's anything else that can work here? Yeah, so if we plug in 3, it's way too big. You get 3 to the 4th, which is like 81, and it's just way too big. And as some people mentioned in the chat, you can directly solve for all the values of floor of A. And so we're not going to show that here, but it's pretty straightforward. You would just move floor of A to the other side and multiply by 2 and then square everything. And so you can do it that way, or you can just notice it by inspection that the only solution is floor of A equals 2. And so if we plug this in for A, as I said, we get A is the square root of 17 over 2. So we have one solution, but we're not done because we didn't check the negative square root. So now let's try the negative square root. So we're going to do the same exact process again. We're going to bound A minus floor of A. And so now floor of A is going to be negative. And so what do people think floor of A can be in this equation? So remember that it's going to be small again because for the same reasoning. And so someone said try -1. If we do -1, we it doesn't work because the expression inside the square root is actually negative. -3. I don't believe -3 works either. Yeah, so -2. So if we plug in -2, we get A is the square root of 13 over 2. And so we know that, I'm saying this is the only one, but you can verify this by trying floor of A is -3. Then you're gonna get that this expression is like less than 0 or something. I mean, it's gonna be greater than 1.
I think you mean negative square root 13 over 2.
Oh, yeah. Typo. Okay, so A is the negative square root of 13 over 2. And so now that we've checked both the cases, we have that the sum of the squares of the solutions are 17 over 4 plus 13 over 4, which is 15 over 2. So our final answer is 17. So the question was, where did the negative square root case come from? So if you scroll up to the previous slide, William, can you scroll up? Yeah, so here we had A squared was the floor of A to the 4th plus floor of A minus 1 over 4, and we took the square root in that equation. And we have to remember that there's a positive and negative root here. Any more questions? Okay, so I guess we'll move on to the next section, which is exponents and logarithms. So first we'll just go over a few familiar properties that you should know. So when you multiply two numbers with the same base, you just add the exponents, you subtract the exponents when you divide. Yeah, so I'll let you read through these. You probably should know all the exponent ones. Maybe the logarithm ones might be new. Number 6.
I think it's right. It's just not the form that you would normally see it in. But I think it's still true.
No, I don't think so. Even if you swap c as the base of the logarithms, it should it reciprocates both the top and bottom. So it should be log AB.
So if you just plug in like c equals 8 or c equals 16 and a equals 2 and b equals 4.
I think it's.
It should be true, I think.
I think
Just
it's
plug
true.
in C with A.
Oh, my bad.
Yeah, sure.
Okay, I guess we'll move on to the next question.
Yeah, so this is the first question we have on logarithms. Yeah, so someone says to try logarithm properties. So we noticed that 225 is 15 squared and 64 is 2 to the 6th. So we can rewrite the equations using our properties. So the first equation is 1/2 times log x plus 1/6 times log y equals 4, and then the other equation is basically the same thing. We're using the power property. So, I think that's slightly wrong. Yeah, so okay, so it should be right now. So yeah, we just used that. So we wrote 64 as 2 to the 6th, and then that we can bring that outside as 6 times log base y of 2. And for 225, it's 15 squared. So we can do log base 2 times log base x of 15. And yeah, so Brian is using a substitution. So we're gonna do that next. So we're gonna let a equal log base 15 of x and b equal log base 2 of y. And so now we can write the equations. The first equation is just 1/2 a plus 1/6 b equals 4. And for the second equation, if we use the reciprocal property that was there on the previous slide, it's 2 over a minus 6 over b equals 1. And so now we have two equations for a and b, and we can solve for both of them. So we can substitute from the 1/2 a plus 1/6 b equals 4, we can say b equals 24 minus 3a. And then from the second equation, we can multiply it by AB to write it as 2B minus 6A equals AB. And so after we do that, we get a, so after we do that, we get a quadratic with just A. And so that after we simplify our quadratic, it becomes A squared minus 12A plus 16 equals 0. And so now remember that our solutions to this equation are actually log base 15 of x1 and log base 15 of x2. So that means that if, so in our final, in the logarithm that they wanted us to calculate, we needed to find x1 times x2. So we can find log of x1, x2. And so that's log base 15 of x1 plus log base 15 of x2. And we know that the sum of the solutions for that equation was 12 because, from Vietta's, because it was a squared minus 12a plus 16 equals 0. And so now we can write that x1, x2 is 15 to the 12th. So I think what people are confused about is why we are doing x1 times x2. So if you go to the previous slide, we needed to find log base 30 of x1, y1, x2, y2. And so what we had was an equation with x1 and x2. So I was just computing what x1, x2 is. And so next we'll do y1, y2. And so we had the substitution b is 24 minus 3a. So that means that we can write that for both. So we can write log base 2 of y1 is 24 minus 3 times log base 15 of x1, and then the same thing for y2. And we can do the same logarithm property to find y1 times y2. Okay, so after we substitute that and use our logarithm property, that's equal to 48 minus 3 times the sum of log base 15 of x1 plus log base 15 of x2. And so that's 48 minus 3 times 12, so that's 12. And so that means that y1, y2 is 2 to the 12th. And so now we just wanted log base 30 of 2 to the 12th times 5 to the 12th, times 15 to the 12th. Times 15 to the 12th, which is log base 30 of 30 to the 12th, and that's 12. So does anyone have any questions? Okay, I guess we'll move on.
So our next question is from the 2016 PMAC, and I'll give you a couple of minutes to think about this one. Does anybody have any preliminary ideas on how we might approach this problem? Yes, we could potentially do that. But in general, for some log problems, it's, oh, thanks, William. So in general, for these problems, it's sometimes easier to substitute a variable as the base of the log to the power of something. So here, the base of the log is 2 in f of x, y. So if we let x equals 2 to the k, then this expression that we see Aaron posted in the chat here gets a lot nicer. So let's just set x equals 2 to the k. Then f of x comma x doesn't have any logs in it. It's much cleaner. It looks like this instead. So now we can throw this back into f of x. So now the expression in the problem gives, oops, yes, let's get rid of it. So now we know that f of x comma x, oh, there is no f there. So basically, we're just taking the substitution x equals 2 to the k and simplifying the expression on the left-hand side. So now we know that 4096, which is 2 to the 12 times this thing, has to equal x to the 13th. So we can write this as a new equation. Two to the k cubed plus 12 is the left-hand side, and 2 to the 13k is the right-hand side. So now we know that the two exponents have to be equal. Yep, and this is a cubic polynomial, and we can solve it by noting that k equals 1 is obviously a solution. We can eyeball that, and now that we know that k equals 1 is a solution, we can divide that out and factor the resulting quadratic. What we get looks like this. So the solutions are k equals 1, 3, and minus 4. Now we want the sum of all possible x, but x equals 2 to the k. So we just plug it back in. And that would be the answer to this question. Yeah, did somebody have a question? Yes, probably. Pumac asks for integer answers, so the answer would probably be 177, but that's fine. We didn't need the empty slide for that one, but for this next problem, we probably will. So there are a lot of logs in this problem. I'll give you a couple of minutes to look it over. So if we take a look at this equation here, the first thing to note is that we have a first equation in terms of only a, and then a second equation relating a and x. And we want to find x, well, the remainder when x is divided by 1,000. So what this suggests we should do is focus on the first equation, solve for a, plug this value of a into the second equation, solve for x, and then obtain our answer for x from that. So does anybody have any suggestions for the first equation? Yep. Well, since everything on the left side is wrapped in a log a, let's just clean that up a little bit first. We'll undo one layer of logs in the first equation. That gives us this. Now, yep, we can clean it up a lot because there's a log 2a inside of the first term, but there is no log 2a anywhere else. So if we set a equals 2 to the power of b, we can clean up the double log. So let's set a equals 2 to the power of b. And put this into the second log. Now this is a little bit ugly. We can clean this up by using our logarithm properties. So instead of using a log base 2 to the b, we can try to rewrite it with a log base 2. So for the first line, for this first bullet, we use log 2b, log base 2b of 2 is 1 over b. And then we combine everything into one single log base 2b, which is log base a. And now we know that this has to equal a to the 128th power. So we can write an equation in terms of b. Well, the initial, we can't put it in terms of a, not easily though. We could potentially do it. It is a bit cleaner this way because the next substitution we're about to make is easier to notice if we make this b substitution first. So let's undo another layer of logs first. Oh, this should probably go on the next slide. So now if we look at this equation, the substitution is easier to see. We can let c equals b times 2 to the 128b and try to solve for c. We can return to the first page after we're done with this question. So if we make the substitution, then we get this equation. Now this equation is a mix of both normal arithmetic functions, addition and division in this case, and exponential functions, which don't mix very well. So it's typically not feasible to solve these equations. But if we take a look at this, c equals 3 is a clear solution. And the left-hand side is strictly increasing, and the right-hand side is strictly decreasing, which means that c equals 3 is the only possible solution. So from here, we can conclude that c equals 3 is the only solution. Now we want to find b. We know that we have this equation for b. Again, we have a mix of multiplication and exponentiation. So the only way that b could possibly be a nice number is if b was 3 times some rational power of 2, since 3 and 2 don't mix when exponentiating. So let's try to make this substitution b is equal to 3 times 2 to the k. Now, if we throw this back into this equation for b, we get an equation for k. Once again, like the previous way we solved for c, we're going to have to eyeball the solution and then verify that there aren't any other solutions through monotonicity. So k equals 3 over 64 is a solution. And there are no other solutions because the left-hand side decreases while the right-hand side increases. So we can safely say that k equals 3 to the power 3 over 64. That means that we can throw this back into our expression for b. And now we know that a is equal to 2 to the power of b. So we know what a is. Now we've solved the first equation and gotten everything we could out of it. So let's turn to the second equation, where we want to find x, because x is what we're going to need to extract our answer. So I think we're probably going to need a third slide. Let's set that up. So now we want to look at the second equation and try to find x. So let's undo the logs twice, because this will get us a clean expression for x. If we take a to the power of both sides twice, then we get x is equal to a to the 256. So now we know what a is, so let's throw that expression in. So we take this thing a couple layers at a time. Let's fix that. So we first find that a to the 256 is 2 to the 12th, and then 2 to the 12th, 2 to the 12 times 3 over 64 is 192. So now x is equal to 2 to the power of 192. And because this is an AB problem, we're going to need an answer from 0, 0 to 999. So this isn't exactly related to equations, but this is a useful topic that we might cover later when we do number theory. But we essentially want the remainder when 2 to the 192 is divided by 1000. So it's enough to find the remainder when it's divided by 8 and when it's divided by 125, the two prime powers that go into it. Now 2 to the 192 is obviously divisible by 8. So let's just find what it is when it's divided by 125. So in short, we know that it's divisible by 8. So we just need what it is modulo 125. So we know by Euler's theorem that 2 to the 100 is congruent to 1 mod 125. This is because the totient of 125 is equal to 100. So that means that 2 to the power of 192 is congruent to 2 to the power of minus 8. And we use a bit of modular arithmetic, 2 to the minus 8 is 1 over 256, which is 1 over 6, because we can lop off a 250 from that, and that is congruent to 21 mod 125. Yep, if you don't know Euler's, this is it's also feasible to just straight up bash this. You can square and cube an appropriate number of times and drop everything but the last 3 digits each time you do it. So we know that this thing is 21 mod 125 and 0 mod 8. So we can use the Chinese remainder theorem to find the unique solution mod 1000. That ends up being 896. Or no, 876 or 896. Let's see. Oh, yeah, it should be 896. And that ends up being our final answer. Oh, that is true. It's a lot easier if you notice that 2 to the 10 is minus 1 mod 25. Although that doesn't help because you need a mod of 125. But you could potentially, that would mean that 2 to the 20 is congruent to 1 mod 25. I'm not so sure. Maybe, I will do a quick Google search for the answer. Check. The smallest integer that 2 to the such that 2 to the n is congruent to 1 mod 125 is actually 100, the largest it can be. So straight up bashing it would be more difficult than if you replace 2 with something else. But yeah, that was our last logarithms problem for today.
Yeah, I guess that ends today's class. The handout is already posted on the website, and you can stay after if you have any questions.